So now let's bring it a little bit closer to home and take a look at what we see on our planet. So if you were to fly to Earth, right, the first thing you would encounter is our magnetic field. So Earth's magnetic field is basically just a giant magnet, right? The Earth quite literally is just like the magnets that you see on your fridge. We've got a North Pole and a South Pole. Now, first of all, I want you to notice that our poles are not geographic, okay? Earth's axis is quite tilted. But if you've ever used a compass, what that compass is doing, that needle is aligning itself with the magnet that's essentially inside the Earth. So the way that this works is our magnets, okay, have a positive end and a negative end. So the north would be, say, a negative, and the south would be a positive. Well, what's happening is the flow of charges inside the Earth goes, right, from our negative to our positive. So what we're going to see here, right, is that our flow of charge is going to be attracted here. It's going to flow around the Earth. And as it flows, it takes any metals, like a compass, and it aligns it, right, with this flow of charge. Now, these magnetic field lines, as you can see, extend out into space. The further you are from the Earth, the weaker it is. The closer you are to Earth or on the Earth, the stronger it is. And it actually forms a shield around the Earth. It protects the Earth from things like solar flares. So the magnetic field is actually quite important. So, like I said, right, the Earth is just a giant magnet. Okay. So what's important to realize here is that this flow of charge is unidirectional, right? It only goes in one direction. So it goes like this, and it comes up, and it just keeps flowing, okay, around and through the Earth. Now, because the sun here is constantly putting out solar wind, which remember I told you is like a solar flare, that solar wind is always pushing against the magnetic field. So because it's pushing against the magnetic field, our magnetic field isn't nice and uniform. It's actually teardrop, right, in shape, because it's getting pushed. Okay. Now, what we call these lines you see here, right, this flow of charge, is a Van Allen belt. Okay. Now, these Van Allen belts, like I said, are very important because it protects us from that solar wind. If that solar radiation were to get into the Earth, it could be quite deadly for most of the organisms that live on our planet. It could truly mess up DNA, right? It can cause your DNA structure to start to mutate. So, truly, our magnetic field is very important. Now, we can see the magnetic field, which this is my favorite part. The magnetic field is sometimes visible, and you may have heard it before. It's called the aurora borealis. Now, what happens is, if you remember, let me go back here. Let's see. Let's go back here to the beginning. So I want you to notice that the flow of charge, right, that goes around the Earth, you see, as it leaves the pole, it comes straight up, and then it's kind of parallel to the Earth, and then it goes straight back in. Now, this part where it's kind of parallel to the Earth, it's not really interacting in a way that we can see it. However, if you are at a high latitude, close to the pole, you see that it's coming into the Earth at an angle. That angle is what we can see as the aurora borealis. So these charged particles are basically hitting the atmosphere, and it causes those particles to get really excited, and it causes them to glow. So you can't really ever see it, right, close to the equator, but you can see it close to the poles. So if you ever go to, say, Alaska, you could see this most of the year. If it's in the northern hemisphere, we call it the aurora borealis. If it's in the southern hemisphere, we call it the aurora australis. But they're the same thing.